Okay, so let's get started. We welcome you to this second lecture on our course in reinforcement learning. We're going to talk about stochastic dynamic programming problems and the dynamic programming algorithm for both a finite horizon and infinite horizon. This is to complement the deterministic dynamic programming material that we covered last time. And then we're going to go into approximation value space, the major method in reinforcement learning, and how it applies in general terms to these problems. So first, we're going to review the finite horizon deterministic material that we covered last time, the dynamic programming algorithm, and we're going to discuss methods of approximation in value space. And then we're going to focus on a particular one, deterministic rollout. We're going to do an example. Rollout is an algorithm that's going to play a significant role in this course. It is simple and reliable, and we're going to cover it in its various versions. Then we're going to go into stochastic problems and the dynamic programming algorithm. We are going to look at an important class of problems which has favorable structure. These are linear quadratic problems, involve a linear system and a quadratic cost function. These are of major importance. They are central in control theory, in dynamic programming, and in reinforcement learning, and in model predictive control. The nice thing about them is that they admit an analytical solution, something that's rare with dynamic programming. And for this reason, for the simple structure and favorable properties and nice solution, they often arise within control theory and reinforcement learning, perhaps as approximations to other more difficult problems. So these are going to be important for us. We're going to do an analytical derivation of their solution. Then we're going to talk about approximation in value space. It's a fundamental reinforcement learning approach. 90% of what we're going to do in this class revolves around approximation in value space, approximating the optimal cost function of the problem by some approximate functions that we can calculate in some way. So we're going to give an outline of that, and then we're going to talk in the second part of this lecture, we're going to talk about approximation policy space. That's the other 10%. Some people would say 20% or 30%, but I say 10%. It has to do with approximating policies using neural networks and the like. Then we're going to discuss infinite horizon problems in place of finite horizon, an overview, and then we're going to revisit the linear quadratic problems in the infinite horizon setting. So we have a lot of material for today, and let's get started with a review. Here is the finite horizon deterministic problem that we have considered last time. It involves an evolution of the states of a system over n time periods. Xk is the state of the system at time k, and it evolves under the influence of control, which we denote by uk. The next state is given by this formula, some function fk, that given xk and uk produces xk plus 1. This is our model of the system. The control is constrained from within some set. Now, the state and control spaces are arbitrary here. That's an important point that I want. They could be vectors in two-dimensional space or multi-dimensional space. They could be chess positions, taking values from the discrete set of all possible chess positions. They could be word strings in the context of a large language model. They can be arbitrary. So all the theory, all the methods that we're going to be discussing, in principle, can be applied to arbitrary types of problems. But of course, for some problems, they may be more convenient than for others. And when you go from xk to xk plus 1 under the influence of control uk, you incur a cost, which we denote by gk xk of uk. And our cost function is the accumulation of the stage cost over the n periods. And then there's a terminal cost at the end that depends on the final state. So this is what we want to optimize overall controls. So for a given initial state, we want to minimize overall control sequences from U0 all the way to UN minus 1. This function here, which depends on the use, of course, but also depends on X0. Minimizing over the use gives the optimal cost function as a function of the initial state. Okay, and we denote by J star. Stars in this course denote optimal. J tildes denote approximate. That's the convention. So that's the problem. And we developed a dynamic programming algorithm for that, which computes all the optimal costs Jk star of Xk. Now, these are the optimal costs of the tail subproblems that start at Xk and go all the way to the end. And the algorithm goes as follows. We start at the final stage with the terminal cost and go backwards. From Jn star, we compute Jn minus 1 star through this minimization here. Minimization of the cost of the current stage plus the optimal cost of the remaining stages. And we minimize over a U that satisfy the constraint set. We do this minimization for all Xk, and for every stage going backwards from n to n minus 1, n minus 2, all the way to 0. And J0 star of X0 is the optimal cost. So at the very end, at the end of the computation, it gives you the optimal cost function as a function of the initial state. So that's the algorithm. And given this algorithm, well, we can store the optimal controls from this computation, but another way that's more conceptually more convenient for us is to construct the optimal control sequence by forward propagation. We start from the initial state now, having computed all these J stars. We compute first J0 star through this minimization. That generates the next state, X1 star, then do this minimization for X1 star, then that gives us U1 star, then U2 star, and so on, all the way forward to the end. So backwards, offline, forward, it could be online. And the thing to notice here, there's a tremendous amount of computation. All these tail subproblems have to be solved for all possible states. And the states can be, it's going to be a very, very large number of states, an infinite number of states perhaps. So this algorithm is practically infeasible for problems of any substance in the absence of favorable structure. And the object of reinforcement learning is to simplify this computation. Now, before I get to simplifications, let's talk about Q factors. The concept of a Q factor is important in reinforcement learning. It is defined for every state and control pair and at every stage. It is the cost of the stage, assuming that I use UK, and then the remainder, assuming that I use an optimal policy, an optimal sequence. So U enters in the first stage, and the remainder is J star. So that's the definition of Q star. Sometimes they're called in reinforcement learning state action values, okay? State action values of cost going forward using UK at the very first stage. So now the important thing to notice is that the optimal cost function, JK star, can be recovered from the optimal Q factor. If you know these Q stars, you can obtain J star. How this is so? Well, look at these two formulas. If I minimize this Q star over U, I obtain the right-hand side, the dynamic programming expression, and that is equal to JK star. So by definition, I have this minimization. So the two can be obtained one from the other. The Q stars can be obtained from the J stars, the J stars can be obtained from the Q stars. So which one you compute and which one you approximate is a matter of preference. Moreover, the dynamic programming algorithm can be written in terms of Q factors, right? I mean, look at this expression. Substituting this into that gives us this equivalent form of the dynamic programming algorithm in terms of Q stars. Going backwards gives you the Q stars as opposed to the J stars. So it's an alternative way to write the dynamic programming algorithm. Now, exact and approximate forms of this algorithm are known in reinforcement learning as Q learning. You will hear this term a lot, and you'll see it a lot in the literature. And they refer to this algorithm and its approximate versions. Now, we'll come back to Q learning as we go along, but I wanted to let you know that there is an alternative form of the dynamic programming algorithm equivalent in terms of Q factors. Are there any questions? You have a question? Yes, the storage requirement for Q learning is higher, as you ask. And the thing to note, however, that this formula is not useful in practice because the amount of computation is overwhelming anyway. So it is useful as a conceptual departure point for approximations. And in the approximations, there is less storage depending on how you execute and how you approximate the algorithm. Okay, so let's now go to reinforcement learning and approximation value space. Like I said, this is a dominant method, an important method, the focus of our course for reinforcement learning. And the idea is extremely simple. In the dynamic programming algorithm, we replace J star, which is hard to compute, with an approximation J tilde during online play. So by hook or by crook, or because somebody likes us and gave us some J tildes, once we have them, it is possible to compute going forward controls to apply in real time. That's all there is to approximation in value space. Replacing the J stars with J tildes, and how you compute those J tildes is an issue of great interest in our course and in general. So once we have this J tildes, we compute the first control. That gives us the next state by this system equation. Then we compute the next control, U tildes of 1, and so on, going forward all the way to the last time period, with the states generated according to this. This is the X tildes are a suboptimal trajectory. The U tildes are a suboptimal sequence corresponding to the J tildes that approximation in value space gave us. So now, how do we compute the J tildes? This is the million-dollar question, and it's one of the principal issues in reinforcement learning. We're going to go through a great number of methods for doing so, but as an outline, let me give you some possibilities. One is to approximate the problem itself, the difficult problem that you have, simplify it, approximate it, and solve it by exact dynamic programming. And then use as J tilde the optimal cost function of the simpler problem. Okay? That's a natural idea. Another possibility, use neural networks, or more generally, some parametric post approximation from a parametric class of functions, where R is the parameter. In other words, we have J star that we don't know. We want to obtain an approximation. So we look at a whole family of functions parameterized by R. R is some parameter that lives in a high complicated space, perhaps. And we use training using data. We generate data from whatever J star or something similar. And then you may use a neural network or some other approximation architecture. I suppose that you have heard of neural network, you've seen what they can do and so on. You're well aware of all this. Your textbook has a whole chapter on approximations using parametric architectures, including neural networks. We're not going to go too much into that until the very end of the course, but I'm going to be assuming that you know what it means to approximate functions by neural networks. Now, another simpler method is rollout. Rollout with a heuristic. So here we use as J tilde the cost function of a heuristic. The same problem, but you apply a control that you know, and you use that online. So let's focus on that for the moment. So here is the evolution of the system. Suppose that we are at xk. We can generate our controls, look at all the possible next states, and we want to have a J tilde for each one of those, right? And now this J tilde in rollout is the cost generated by some heuristic, running a heuristic from these states. So that's how rollout works. At the current state, consider all controls, consider add on top of this cost of this stage the cost of the heuristic. You run the heuristic, you evaluate its cost, and you have these numbers here. And you select the lowest number and the corresponding control to apply. That takes you to the next state, and you do the same thing. Again, roll out, going forward. So here it is. Upon reaching xk, we compute for all feasible u the corresponding next states. Then from each of the next states, we run the heuristic and compute the heuristic cost. And instead of J tilde, I'm denoting by H to emphasize it's a heuristic. We're going to call this the base heuristic. Now we apply U tilde K that minimizes the heuristic Q factor. You can view this as an approximate Q factor. Remember, Q factors are state action values involving the first stage cost and then the optimal cost after that. Now, heuristic Q factor is we use H instead of J star. Okay. So you can view this as a Q factor. Indeed, it's convenient to view it that way. And then we generate the next state and repeat. So first stage minimization, roll out forward, go to the next state, roll out forward, go to the next state, and so on all the way to the end. So let me illustrate this with an example. Okay, so let us now illustrate rollout by using the traveling salesman example that we had used in the previous lecture. Again, here we have 4 cities, A, B, C, and D, and there are travel costs associated with going from one city to the next, and they're given by this matrix here. So from A, I can go to B at a cost 5, to C at a cost 1, and to D at a cost 20, and so on. And we want to find a tour that starts at city A and goes to, returns to city A after going through all the other cities once and only once. So we did the dynamic programming solution of this problem in the previous lecture. And now we're going to use rollout to obtain a suboptimal solution. And for this, we're going to use as base heuristic a nearest neighbor heuristic, whereby from every city, we act greedily and go to the closest next city that's eligible and has not already been visited. The illustration from is given here. We start at the initial city, and after reaching this state, traversing all these cities. We look at all the possible next cities, and from each one, we run the nearest neighbor heuristic, and we compare these three trajectories in terms of their cost and go to the next city that corresponds to the best trajectory. So let's illustrate the nearest neighbor heuristic and the rollout algorithm that's based on it. Starting from A, let's generate the trajectory using the nearest neighbor heuristic. So here we consider the three neighbors, and the closest one is C at a cost of 1. So we next go here. Then we consider the two eligible neighbors, and we go to the closest one, which is D. And then there's no other choice to go to B and then to A again. And the cost of this base heuristic is 1 plus 3 plus 4 plus 20 equals to 28. So now let's do rollout by starting from A and using the nearest neighbor heuristic as base heuristic. Here we consider the next eligible cities and run the base heuristic from each one. So from this state, we consider the two eligible next neighbors. The closest one is C. So we go to C, and then we go to D, and then to A. And the cost of this tour is 5 plus 1 plus 1 plus 20, so that's 27. From here, so we consider city C and the nearest neighbor heuristic going from it to city A, and the base heuristic gives us this trajectory, and the overall trajectory has cost 28. So we prefer this one to this one. And then let's go to the next possible city, which is D, and consider the nearest neighbor heuristic from here. So we compare these two. The closest one is this one, and then there's only this one to go to and this one. So the cost of this trajectory is 63. So we have 27, 28, and 63. The best city to go to according to the rollout algorithm is B. Now here, again, we do the same thing. We consider the neighbors of B and then run the nearest neighbor heuristic from each one and try to pick the best one. So here we have two neighbors, C and D. And then we run the nearest neighbor heuristic from here. There's nothing to compare. And the cost of this trajectory is 22. And then we consider also going to D and run the base heuristic from here. And the cost is 7. So this city is better. So the rollout algorithm will take us from here to here. And then, again, we do the next step of the rollout algorithm, but there's only one possible city to go to. So it takes us here and then to A. So the rollout trajectory is this red one. And this cost is 5 plus 4 plus 3 plus 1, which is 13. So we started out from 28, went to 27, and then to 13, each time generating a better trajectory, which is actually a generic property of rollout that we are going to discuss in the future in a more theoretical setting. So that's the illustration of the rollout algorithm. And notice a qualitative difference from the base heuristic. The base heuristic is greedy, is blind. It looks only one city forward to the next closest city. On the other hand, rollout looks into the future in each one of its steps, and so it has this far-sighted property that's actually at the root of its improved performance. So we are going to revisit the rollout algorithm in the context of other examples, and we're going to discuss its theoretical properties after the fourth lecture, after we finish this series of four lectures and go to the fifth lecture. Let me now go to the stochastic dynamic programming algorithm. Okay, so we similarly have a dynamic system that evolves over n stages. The states are called xk at stage k. The controls again are called uk, but there's also some uncertainty in the system equation. So given xk and uk, xk plus 1 is not fully predictable. It's random, and its randomness is controlled by this uncertain, this random quantity wk. We call it disturbance. So that's the system equation. Wk is random with the given probability distribution that depends on xk and uk. It could be, depending on the context, physical noise, market uncertainties in the context of an investment problem, demand for inventory in a supply chain problem. In a factory, you may have unpredictable breakdowns that affect the evolution of the state. So all of this can be represented by this W. Now, when you make a transition from xk to xk plus 1, there's also a cost that's incurred that depends on the random disturbance. So this cost is random, and the cost function that we have is the accumulation of all the stage costs plus a terminal cost. But this quantity here is random because of the W's. So we take the expected value of this, which is a number, and that's what we minimize. Now, the other important thing to note is that here it's important to minimize over policies. Mu0, mu k plus 1, not sequences of controls, but sequences of functions of xk, or what some people call strategies. Each one of these mu's, mu k of xk is a function of xk, and as a function can be used as a lookup table. So when you reach at xk, you look up the table for the control to apply. That's the nature of the policy. A lookup table for every stage that tells you what to select when you are at any given state. Now, an important point is that using policies as opposed to sequences of controls gives you a genuine advantage in stochastic problems. The reason is that it doesn't pay to select blindly a sequence of controls when you are at x0, because you don't know, even if you choose that sequence, you don't know what the next states are going to be. It's better to wait to see at what state you land, and then pick up the control appropriately using this lookup table. This is called feedback. Choosing controls with knowledge of the state, and it's beneficial because of the stochastic nature of the problem. For a deterministic problem, you don't have to use these policies. For a stochastic problem, this is essential and makes the problem considerably more difficult. And basically, the only way you can address problems like that is by dynamic programming, not other methods. So for a given initial state, we want to minimize overall policies, which we call pi. We denote pi generically. This cost function. Plug in the policy. This becomes a random number, takes the expected value, and this gives you a number that depends on x0, and of course the policy. And the optimal cost function is the minimum of this expression over all policies. That's J star of x0. And the optimal policy is the one that attains this minimum. So that's the formulation, similar to a deterministic problem, except for this randomness, it necessitates the policies, and we have a cost that's defined by an expected value. On the other hand, we still have the stage-wise character of the problem, and we can apply ideas based on the principle of optimality. You have a question there? How do we model the WKs? You have to know the distribution, either given to you in closed form by formulas or through a computer simulation. You need to have either a computer model or a mathematical model. Everything I'm talking about assumes either a mathematical model or a computer model. A computer model, of course, is a mathematical model. It's just buried inside the software. And there's no difference between the two. And from a mathematical point of view, they're exactly the same. How do we, in practice, how do we obtain? Through a lot of, the way you do all kinds of modeling in engineering. You collect data and you try to fit uncertainties to this data and so on. It's problem dependent. Okay, so the ideas of the principle of optimality apply also here. And the stochastic dynamic programming algorithm has a similar structure as the deterministic one. It produces the optimal cost of the JK stars depending on state of the tail subproblems, all the tail subproblems that start at all the different states and stages. It starts from the terminal cost and it goes backwards in time using this formula here, which is the same that was the one we had before, except it involves expectation. Again, we have the cost of the first stage, the expected value of that, plus the optimal cost of the remainder from the state where we land, again, expected value of that. So the computation is similar. Start from here, go backwards, and at the last step, we obtain J0 star of X0, which is the optimal cost. You can prove that rigorously mathematically, but intuitively, if you think of the principle of optimality, it becomes fairly clear. Now, with this computation, you can also obtain the minimizing control for every state, and you can piece those together into an optimal policy, a lookup table that for each xk gives you the corresponding minimizing control. Alternatively, you can use a forward computation after you have computed all the J stars. Assuming that you have all those, sequentially going forward, we observe xk, and then we apply the corresponding control. Now, in all this, we assume that we observe the state. Once we apply control, then we wait for the next state, and we observe it exactly. And then once we have a policy, we use a lookup table to see what control we are going to apply. Now, if we don't have the lookup table given to us, we can construct online the minimizing control through this computation. So there are a number of issues here. For this minimization, you need to have the J stars. Then you need to compute the expected value of all this, which may be a substantial computation. And then you need to do a minimization of this expression over OU. That again may be a substantial minimization. This involves a horrendous amount of computation. This involves, given the J stars, this involves an amount of computation that may or may not be overwhelming. If it's overwhelming, you have to simplify it somehow. Reinforcement learning deals with all these things, simplifications to avoid the onerous computation involved here and here. Now, the stochastic dynamic programming algorithm can also be used as an analytical tool to obtain analytically the optimal solution of some selected class of problems. These are the lucky problems, the ones that have favorable structure and the mathematics works out nicely. And a very important class is the linear quadratic problems. And we're going to talk about that now. Okay, so let's assume a one-dimensional linear system of this form. The next state is obtained by is the sum of a linear expression of the state. A is a given scalar, multiplies the current state. B is a given scalar, multiplies the current, the control that you apply. And there is a random disturbance, which we assume to be zero mean and having some variance, okay? Now, this is the system. The cost over n stages is quadratic. Quadratic at each state, Q and R are positive given numbers, multiplying the square of the state and the square of the control. And there's also a quadratic terminal cost. And the dynamic programming algorithm specialized to this problem starts with this function here, the terminal cost, generates KK star by this computation. Now, it turns out that this computation can be executed in closed form. You can get formulas for it. And the main result is that JK star of xk is a quadratic function of the state, with k of k being a number that you can compute, plus a constant number, which doesn't matter, but you can compute that too. And moreover, the optimal policy is a linear function of the state, where LK is a number that can be explicitly computed. So quadratic optimal cost for the tail subproblems, linear policy, optimal policy that's linear. And the KK and the LK can be obtained with a dynamic programming algorithm. There's another interesting fact here, is that the optimal policy does not depend on the distribution of W. It's the same whether the problem is deterministic or stochastic, as long as the expected value of the disturbance is zero. This is an instance of what we call certainty equivalence. It means that the optimal policy remains the same if the uncertain quantities are replaced by their expected values. In other words, if we knew exactly this optimal, this disturbances to be equal to their expected values, we would not change the control that we apply. The control does not depend on the distribution of WK. Now, this property is very nice, but it's also rare. There are only few problems that have this property. On the other hand, in reinforcement learning, often we use this property as an approximation for other problems to simplify the stochastic structure. Now, the other thing I want to note is that I'm going to talk about this result for a one-dimensional case, but it holds much more broadly for multi-dimensional linear quadratic problems, where xk belongs to an n-dimensional space, uk belongs to an m-dimensional space, and the scalars a, b, q, r here are replaced by matrices. Similar results hold, and the computation is pretty similar, but the one that I'm about to give you. So what I'm going to do now is do this computation going backwards from the terminal cost function all the way to the beginning and show you how this KK and LK are computed. It's a long but straightforward calculation. The Jn star is Qxn squared, right? So the first step of the dynamic programming algorithm does this calculation here. We plug in for Jn star Qx qxn star, or the argument here. And now what we have to do is carry out this minimization. So let's expand this quadratic term, the square of this one, the square of wn, and the cross product term. And now let's use here the fact that wn minus 1 has 0 mean. So this term is eliminated. And this term is a constant. This is the variance, expected value of wn minus 1. It's a variance, but it's a constant number. So now we have to do this minimization of this term here and add the constant term. This does not depend on un minus 1. The stuff that depends on un minus 1 is this here. And it's a quadratic minimization. Quadratic minimizations are easy to do. How do we do them? We take the derivative of the expression, set it to 0, and then solve for the minimizing variable. So that's what we do. We set to 0 the derivative of this expression, okay, which is this, taking the derivative of this, which is this, set it to 0, and that gives us un minus 1. We solve for un minus 1, and we obtain this, with L, the coefficient, being given by this, okay? Solve this equation here for un minus 1, and we get this. So all of this can be computed. Moreover, we can take this optimal and plug it in here, and then do all the algebra here. And what we're going to obtain is a quadratic function of xn minus 1, where the coefficient of the quadratic is given by this formula here, okay? Basically, linear control gives you quadratic cost. Quadratic cost can be, after we collect the terms of the quadratic cost, we obtain this expression. This expression here, with kn minus 1 given by this. So now we have ended up with a j star n minus 1, which is quadratic, and we can play the same game. Minimize the quadratic, obtain linear control, plug back in again, obtain another quadratic, and so on. And going backwards, we obtain this solution, the entire solution of the problem. The optimal cost of the tail subproblems is quadratic in the state, plus a constant term that depends on the variance of the W's. And the optimal policy is linear, and the coefficient of the linear expression is given by this. The case propagate backwards according to this. The linear cost coefficients, the linear control coefficients depend on the k plus 1 variables according to this formula. So all of this is a simple computation going backwards, but it generalizes to the case where you have a multidimensional problem. Are there any questions here? I urge you to study, go through this computation, even though it looks a little formidable. It is actually very simple conceptually. It's just a matter of taking derivatives, collecting terms, and so on, and everything works through from one stage to the next. Yes?
Then a question about the stochastic setting. So if at each round k is the probability distribution of W allowed change in the setting.
You need to know W. That's what, yeah. Is that your question? In a generalization of this problem, you can have W's having different distributions at every stage, but you have to know them. And the A's and B's also can be time varying. There's a lot of generalization that's involved here, but of course you have to know the system itself, A and B. You have to know the cost, Q and R, and you have to know the fact that W has 0 mean. Okay, that's important. Now, in a more general version of the problem, the W could have an arbitrary mean, but known, okay? That's the important thing. And then these formulas will change a little bit. But the same derivation applies. Okay, so I'm coming to this question, generalization of the linear quadratic problem. Some observations. The solution does not depend on the distribution of WK, only on the mean. In other words, we have certainty equivalence. The stochastic problem can be replaced with a deterministic problem where the uncertain quantities are set to their expected values. The solution method generalized to multidimensional problems, non-zero mean WK, and so on. It generalized to an infinite horizon, not just a finite horizon. It generalizes to problems where the state is not observed exactly at each step, but rather is observed partially through linear measurements. In stochastic dynamic programming, we assume that we observe the state xk exactly before we apply control. However, the linear quadratic, but later we're going to talk about problems where the state is not observed exactly, but rather is inferred through measurements. Not exactly, but within a probability distribution. So we're going to go belief distribution. So this linear quadratic solution generalizes to problems like that, where you measure the state through measurements that have a linear structure. And then the solution generalizes as follows. The optimal policy is this: apply control that's linear, uses the same linear cost coefficient as the deterministic version, but multiplies not the state, which we do not know, but rather the expected value of the state given the measurements. Now, this expected value is provided by what's called an estimator. And in the case of a linear quadratic problem, this estimator is called a Kalman filter. Some of you will have heard this term. It's a very famous algorithm used for estimation of the state of linear systems using linear measurements. Using this Kalman filter, we can obtain this expected value, and then we have to multiply this with the same linear policy coefficient as for the deterministic problem. So we have essentially a form of certainty equivalence extending to the case of partial measurements. So that's why this problem is so useful and so widely used, because it works out very well. But the important thing to note also is that it can be used as a starting point for approximations in other problems that do not have as favorable structure. And this is what reinforcement learning does to a great extent, and other related methodologies, such as model predictive control. So that's the next bullet here. Linear quadratic problems are often used as a starting point for other lines of investigations and approximations. For example, problems with safety constraints that arise in model predictive control, self-driving cars and things like that. MPC is the acronym for model predictive control. Also, problems with control constraints sometimes are approximated with unconstrained problems, where the quadratic penalty is used as a substitute for constraints. Then linear quadratic problems are also used in contexts where the coefficients of the system, the A's and B's, are either not known exactly or are changing over time because the environment changes. Then you have to estimate them, and then you may apply linear quadratic control based on the estimates. So there are many different ways that this linear quadratic problem enters the approximate dynamic programming and reinforcement learning landscape. But also for us, these linear quadratic problems are going to serve an extra purpose. They're going to be used for visualization and geometric understanding of methodologies that are used in reinforcement learning. We're going to understand reinforcement learning through visualizations of these linear quadratic problems. And this is going to be a principal theme for the next lecture. So we'll come back to those. But now let's talk about approximation in value space. I mentioned that approximation in value space is simply dynamic programming where J star that we don't know and we don't want to compute is replaced by some J tilde, some approximation. And the way this works is at the current state, we do this minimization involving the cost of the first stage and involve an approximate cost of the future to the extent dictated by this J tilde. Take the expected value in case of that we have a stochastic problem, and then minimize over UK. So that's approximation in value space with one step look ahead. And it's an online play algorithm. Offline training gives you this J tilde. Online play is this control calculation going forward. But there are other potential approximations in this formula here. There's the cost to go approximation, this J tilde, which I mentioned. Sometimes this expected value is difficult to compute, and we may want to approximate it by some limited sampling, some kind of simulation. There are a number of ways to approximate. Sometimes this minimization is difficult, and we may want to simplify it. So there are three approximations in this landscape: cost to go approximation, expected value approximation, and simplified minimization. And most of our course is going to deal with methods for dealing with doing these approximations. There are a number of different ways. And we're going to be dealing also with another version of this approximation value space that involves multi-step look ahead. Here we look forward one step and we approximate the future after that first step. In multi-step look ahead, we look forward several steps and then take the approximation at the end. Like in chess, like in AlphaZero, we look at the look ahead tree over many moves, 20 moves, 30 moves, whatever. And then we use a position evaluator to approximate the future. So multi-step look ahead is the version of this formula that I'm showing here. At a state xk, we consider the cost of the first L steps, 2 steps, 3 steps, 50 steps, L steps. This is the accumulated cost of all these steps. And then we approximate the future after the L steps with some J tilde function. So for L equals 1, we obtain this picture here. For L greater than 1, we obtain this picture here. And what we do here at the state xk, we solve this minimization problem that involves an optimal control for the current stage and also optimal policies for the remaining L-1 stages. Now, this is a dynamic programming problem, right? It's a stochastic dynamic programming problem, but with fewer steps, L steps. Okay? So this L may be, N may be 1,000, L may be 5 or 10. It's an easier problem to do. And moreover, we have to solve it for a single initial state. So look ahead minimization, cost to go approximation. And similar questions arise. How do you compute J tilde? How do you approximate this expected value if you have to for a difficult problem? And how you simplify this minimization in case this minimization is difficult. That's 90% of reinforcement learning. And here are some thumbnails of methods that we're going to be using. And I'm showing the case of one-step look ahead, but there's a similar picture for multi-step look ahead. Remember the 3 approximations. Now, J tilde can be approximated with several different methods. And I'm listing some, and we're going to visit probably all of them to some extent. One is by using certainty equivalence. Simplify the problem and replace it by a deterministic problem. And solve the deterministic problem and put J tilde as the cost function of that simpler problem. Problem approximation is similar. Solve a simpler problem uses cost function for cost approximation. Rollout, using the cost of a heuristic. In model predictive control, there are special methods for computing this J tilde. Parametric approximation and neural networks. This is also a very popular method. Approximate this J tilde using data, using the result of our neural network training, and then use that in here. Aggregation is another method which involves simplification of a high dimensional problem using a lower dimensional problem, and we'll probably get to that at the very end of the class. So there are many, many different methods, variations for this J tildes. There are also methods for computing expected values, particularly by simulation. If you have to compute an expected value by simulation, that's very time consuming. You may simplify this minimization and do your simulation more accurate for the most important controls and less accurate for others that seem not very, very promising. Monte Carlo research is a method of this type, and it has proved important in a number of contexts. Approximate minimization. Well, this minimization may be over continuous space, an infinite number of controls. We may discretize the controls. Use discretization and use also pruning of the set of controls, pruning out some controls that on the basis of some preliminary computation, they don't seem very promising. Just drop them. So we're going to be talking about methods in this entire landscape. And as an example, let me focus on rollout. Rollout extends to stochastic problems as well. At a given state, we generate all possible controls, and then we generate all possible random disturbances to get to the next state. And then we use a base policy to look into the future, all the way to some number of steps, M. And then we use a terminal cost function approximation, this J tilde, which involves now, it involves a terminal cost approximation, but also the cost of the rollout policy here. And we select the optimal control, and then go one step forward, and so on. So it's pretty similar to what I gave earlier for deterministic problems, except that there is this W here, and this expectation of the cost of the base policy may require some extra computation that could be substantial. So into the future, we're going to be using this picture a lot. It's going to be an anchoring picture. We're always going to be coming back to that and pointing where each method fits in this picture. Yes?
And best practices which to validate the model with so many approximations,
Validate the model. Okay. Here in this course, we assume that the model is given either through a computer model or a mathematical model. The question of constructing a model is a subject in what's called system identification or learning a model, whatever people in artificial intelligence use a number of names, but we are not going to be covering model construction, except some superficial remarks about using neural networks, input-output data to construct models. Our class is not going to focus on model construction. It's just we have enough to cover as it stands. Okay, I have a last slide before the break. This is a comment about the use of approximation architectures and neural networks. We're going to be using them in this course as cost function approximators or Q-factor approximators. And here's the picture for cost function approximation. We have a target cost function, J, which we want to approximate, J of the state. And we want to obtain an approximation from a family of parameterized functions. R here is a parameter. This parameter may have 1 or 2 variables, or it may have 2 billion variables, okay? It can be, it's a vector that involves many components, potentially. And what we want to do is find the R for which this corresponding function approximates well the target function. So target function approximation, and adjust the parameter, tune the parameter so that this is close to that. So generally, how do we do that? We collect training data, which is pairs of x's, states, and costs associated with them. Many of them, hundreds or millions of those, and we plug them into a specialized optimization algorithm that does this matching. These algorithms are called least squares methods or gradient descent. There are various optimization algorithms that find the optimal R in terms of the approximation of this J tilde to J. There are also some other methods that belong to the class of temporal difference algorithms. These were quite famous and quite the object of a great deal of research in the early years of the field, but not anymore. It's usually this kind of thing involving least squares, gradient descent, deep neural networks, things like that. And talking about neural networks, you've probably seen this in other places. Let me explain the structure of a simple neural network. Remember, we want this neural network to represent an approximation to a target cost function. So here we feed in the state. There's an initial calculation that encodes the state in some other space, and this encoding we call y sub x. It's some function that's problem specific. And then we have a layer, a linear layer. We do a linear transformation on this y sub x that involves a matrix A and a vector B. Now, these are tunable. They are parameters that we need to pick. And each scalar output of this layer goes through a nonlinear layer, a sigmoidal layer, or something something related, RLU, whatever. There are many different sigmoidal layers that people use. And we obtain now a function of x and of v. V is the set of parameters of the linear layers, A and B. And all of these are linearly weighted at the final layer with a parameter C. So there are 3 types of parameters here in this structure: A, B, and C. And this is the approximation to J that we're going to use. So after we have trained the neural network and we know this A, B, and C, we plug in the state and out comes the cost approximation. That's how the neural network is used in practice. So if we want to find a J tilde, we first train the neural network, and then for a given state, we give it to the software and cranks out a cost approximation. Now, this is a single layer. Nowadays, neural networks have many, many layers. Deep neural networks have hundreds of layers. And moreover, there are other types of neural networks, the transformers, the GPT type of networks, which have a different structure than that. They do the same kind of job, but they have a different structure. And the future may hold still other structures. What you're doing here is pretty much heuristic, okay? You play around with the different structures and hope for the best. And from simple neural networks of the past that involved only 1 or 2 layers, we went to deep neural networks that involve hundreds of layers as computational power has increased, and you are able to train these things. And then we have arrived at transformers. which is still a different kind, another kind of network. And the future may hold, again, other architectures, which in some cases may be specialized for a particular type of problem. One type of architecture may be better than another. A problem that involves large language elements, like language components, is likely to have a transformer, GPT, in there. However, a problem that involves steering a car through a self-driving car, a GPT may not be useful. I wouldn't trust it, okay? Particularly if you can accept input from the passenger. I'm trying to be humorous here. So I'm giving this picture. Keep this in mind. You know a lot about this picture, but we're not going to visit this picture for quite a while. We assume in the background that approximation is done by either a neural network or something similar. So are there any questions? Okay, we'll be back in 15 minutes.
And now shift gear to shift our attention to a major alternative of approximation in value space, which is approximation in policy space. As you may recall that in approximation in value space, what we do is we try to get some approximation J tilde to approximate J star. However, that's not the end of the story. Once we get J tilde for all stages, what we really need in real-time operation is to have control. So we still need to carry out this calculation like one-step look ahead, a multi-step look ahead, which would involve minimization, expectation calculation, which can be a lot of calculation. So the alternative to approximation in value space is approximation in policy space, whereby we directly approximate a given policy. What does that mean? Means we select the policy by optimization over a suitably restricted class of policies. Well, given an optimal control problem, we don't really know how the optimal policy looks like, right? Then suppose that out of some approach, we get some training data, which is the state control pair. So it can be given by an expert or even by an expert computer or software, as we will come to this point shortly. So given those training data, we may design a neural network that try to mimic this training data pair that given as input state and directly spells out the control and try to have this neural network approximate as closely as possible the training data. Then essentially we have restricted our attention to this particular neural network. So the restricted class is usually a parametric family of policies that depends not only on state, but also on this parameter R of some form. And this is the form is decided by us, by the designer, where the RK is a parameter. So in the context of neural network, this R would be the weight of all the neural network. So the method used for optimization or offline training to get this R that approximate well the training data include random search. This is one of the possibility. But nowadays, one of the prominent approach is policy gradient type of method. Essentially, by approximate well the mu k with the training data, we're going to construct some cost, least square type of cost typically. So this least square type of cost, given the current parameter value, we compute the gradient with respect to this least square cost and modify the parameter to the direction that reduce this least square cost. This is the policy gradient method. And it can also be the machine learning or classification type of method, which we will discuss later in a later course, a later lecture. So the important advantage of this approach is that after the offline training process completed, we will have an parameter R for each state fixed. So this thing will be fixed. Then during the real-time operation, the system or the environment at a given state xk, we directly plug in to the controller, whereby recall that this RK has fixed since we have completed the training session, and it will directly spells out a control for us to apply. So no minimization calculation and those sort of thing, calculation of expectation and so on is needed. So again, if we assume this is a neural network, then directly given a state, it is the input, then you feed forward this, do the feed forward calculations through the different layers of neural network, the output gonna be the control. That's it. So it's relatively lightweight calculation compared with the calculation of minimization, expectation, and so on. However, there is an important disadvantage. That is, it does not allow for online replanning. Again, as I said, the process of finding this RK is offline training process. It involves a lot of calculation, a lot of optimization calculation based on a lot of training data. So you cannot really do this during real-time operation. Like if you have an autonomous vehicle, you cannot just, okay, you train the vehicle based on the expert driver on a dry road. So then you fix this parameter for steering control of the vehicle. All of a sudden, if the ground, if it's gonna rain today, or it's a slippery, icy road, then the training data that is tailored for the dry driving condition will not apply, right? Then you are in trouble. Whereas in some of the approximation in value space method, it is possible to do online replanning, especially rollout type of method. So this is one of the drawbacks of approximation in value space. The other drawback is it does not involve Newton's method, and the significance of Newton's method will be clear in the next lecture. Okay, as I mentioned earlier, the approximation in value space, after we computed J tilde, is not really end of the story. It's not like what we need is a J tilde. What we really need is a control. So we still need to have the calculation during the real-time operation, whereby given the current state xk, we calculate for each uk the expectation that involve the current stage cost and the computed optimal cost to go, and then minimize among them. So approximation in value space is primarily an online playing method with offline training used optionally to construct the cost function approximation for one-step or multi-step replanning. Whereas approximation in policy space is primarily an offline training method. So once we finish the training process, during the online real-time operation, everything, the calculation become relatively lightweight compared with this one. However, still, the policy that we obtained through approximation in policy space can still be applied within the framework of approximation in value space, especially when applying rollout type of method, right? Because as you may recall that in rollout, we need a base heuristic. We need a heuristic to solve the problem. So the policy obtained through approximation in policy space can be used as basic heuristic. So, and this is one way that this policy obtained through approximation in policy space can be improved. Vice versa, that we can also go from approximation in value space to approximation in policy space. Because after we compute approximate cost to go, J tilde, during online real-time operation, we still need to do this minimization calculation and various expectations. And it is through this minimization, it defines a suboptimal policy mu tilde. So through one-step or multi-step look-ahead minimization. What if this one-step or multi-step look-ahead minimization is still too much to compute in real time? Because after all, it involves expectation and minimization. How can we make this calculation simpler? Well, one way is to use offline approximation in policy space to learn this mu tilde k. So remember in the previous slides, I alluded to that in approximation in policy space, we need this target data, right? One way this target data can be generated is to use this minimization calculation. So suppose that we have already through certain approach computed J tilde k plus 1. If we want to directly use it in real time calculation, we need to carry out this minimization calculation, which may be too much. What we can do is just collect a lot of states, xks, whereby for each xks, we calculate this minimization calculation, one step look ahead. Since it's offline, we can afford better calculation of expectation and precise minimization here in order to find what is the control. So this control would be the one that given xks, this mu tilde k generates, right? This process is carried out offline. We collect a lot of sample pairs where this Q gonna be huge or large, depends on the problem size. And then using those as target data in order to train a policy where this policy is parameterized by RK of certain form. So this RK is the thing we want to learn. Then we estimate or compute a parameter RK such that it minimizes this least square error. So we try to find an R such that this, again, if you think of it as a neural network, you try to have this neural network generate as closely the control U as the sample at the sample state point. There are two things I want to clarify or mention to you. One is that in this training problem, we use this least square fit, right? And in the literature, this, of course, often called cost. It's a training cost. It's different from the cost of the dynamic programming problem. So it's a different thing, right? So this is the cost that characterizes how close the policy, the randomized policy, this parametric policy mimic the target control UKS. So this is the first point. This is a different cost than the cost in the dynamic programming. A second thing is, as I mentioned earlier, this Q can be large or even huge. And R can also be large or huge. So it's not possible to solve this least square problem all together, all at once. So what people do is, instead of considering all samples Q, let's say a zillion sample all together, you just have a bunch of 10 or 50 samples. And based on this 50 sample, you change slightly the parameter, and then use another 50 sample and change it slightly. This process, often people also refer to it as learning, and it's different meaning of learning than what we call, right? So learning is a different meaning in this context, and I just want to bring that up. Yes?
How do you collect the sample then?
Oh, you mean here? Well, there are a lot of ways. For example, if you have the simulator, the xk can be basically starting from some state. You apply the control and apply this particular control to the system. You're going to generate a new state, and you apply the control again. You're going to generate new state. So basically, it's going to be a trajectory, and then you sample a different initial point and collect the trajectory. Yeah. That's a matter of choice. For example, you can use the control that is given by this formula, right? In this minimization. So the trajectory would be generated under the policy that we try to learn. But it can also be other policy, because there is a issue that if you only focusing on trajectories or samples that can be generated under a given policy, you're going to face the problem of under exploration. Yeah. So this is a different matter.
Question is because to train like approximate to the policy, we need somehow like a policy section. Because when you collect the sample.
Yeah. Here, the whole point is that given this J tilde, and we want to mimic this policy mu tilde, which is obtained by approximation by one step look ahead, let's say. So the state control pair, given a state, the control is calculated by this expression. Is it clear? Because there is a target policy we try to learn. Yes?
The main point of this is that not all the approximation and minimization associated with approximation.
Sorry?
Is the main point of this approach to get around all the
Exactly. So basically, after we have this J tilde, if we only have this J tilde, when during the real-time operation, we will still need to carry out this minimization calculation, which can be costly. And we need to, for each minimization, in the minimization, for each UK, we need to compute the expectation. So this whole thing can be costly. For example, if we have 10 different control to select, that means we need to calculate 10 different expectations. So this expectation may cost, let's say, 2 seconds. Whereas in autonomous vehicle, you have only 2 milliseconds to react. And that's too much. So we need to basically, instead of calculate this on real time, offload this calculation offline. Yes? Yeah. Sorry? Yeah. Exactly. For all the case. So that's why we call it offline training. If we use the AlphaGo type of AlphaGo as an example, as you may know, that the offline training we refer to is the process that all the engineers, software experts, and so on back in London, they spend months and months and training the algorithm, training the network, and so on. That's offline training. So there's not really very strict time restriction, because if the training did not finish today, fine, you come here tomorrow and let the computer run it, right? Whereas the online play is the part that when the AlphaGo actually brought to Korea and start to play with Lee Sedol. You cannot have Lee Sedol sit there for 2 hours where you tune some parameter, right? There's restriction on time. That's why we call it online play, because it's during real time playing. The decision need to made, all the calculation need to be done, the minimization, expectation, and so on. All those things are done in real time. That's why we call online play. Yes?
How do you go about answering that question, which is your algorithm, what you develop, how do you ensure you're exposing it to enough variation so that when it's performing?
That's a fundamental problem about exploration, right? How do you explore the state space? Because even the number of Q is gigantic, it may not cover all the state space, right? So, but this is a subject of its own matter. It's important, but we don't consider it here. Yes?
To correlate all the space with the objects with CSV 550, like, and or
Sorry?
you have to correlate the policy space with NPR for approximation. NPR, CSV 550, trying to match this for the CSV 550 to the baseline observed.
Okay, so it doesn't really apply because let's say if we are considering approximation using neural network, then this basically this minimization calculation is an unconstrained continuous quantity optimization problem. So everything is continuous. There is nothing, okay, this is a gigantic dimension, could be like nowadays all the GPT stuff is 200 billion, but it's continuous. So it has nothing to do with what you described. Yes?
It's like these examples, like so we already consider like for example like unconstrained problems, so that's like a 10 scale. So for example, like some autonomous vehicles, right? So they have some building constraints, like you can have like like thread, and also the length of the roads. You cannot cross the road. All these cost functions.
Well, of course, this cost function itself, if we consider it as real valued function, for example, then all those hard constraints like the length of the road and so on may not be explicitly encoded. But generally, you may consider all those constraints all together with this function as what we call extended real value function that have infinity in those forbidden area, right? Alternatively, you can put a huge penalty on those places where it's not allowed. So there are alternative ways or different interpretations. But in methodology of MPC, typically people use constraints so constraints together with this function, we suppose this is a real value function. So those two together act as a terminal cost. Yeah. All right. So that's enough for approximation in policy space. Let's give a brief overview of an infinite horizon problems. Now for infinite horizon problem, similarly, starting from some state x0, we apply u0, we move on to the next state and so on. However, here are several major differences that is different from the finite horizon problem. Recall that in finite horizon problem, after n stages, after we make n decisions, the process terminates, right? No further decision are needed. Whereas in the infinite horizon problem, this process continues indefinitely. into the future. So practically, this means that the problem is very involved so many stages. You might as well just consider it infinitely many stages. So this is one difference. The second difference is that typically the system that describe how the state evolve over time is stationary, by which I mean, compared with the finite horizon problem, you see here is no subscript k. So this function depends only on state, control, and this random disturbance, but not on the stage. Because if you are at a state, at initial stage, you are facing an infinite horizon problem. And if you are at the same state at stage 5, you're facing exactly the same problem. So that's why typically we consider infinite horizon problem, we refer to the case where the system dynamics is stationary, does not depend on stages. And similarly to the finite horizon problems, a policy is a sequence of functions where each function satisfies control constraints for all x and k, except that now the sequence of function, the length is infinite, because for each stage, we need to have a function to decide. And another difference is that, okay, so the stage cost also similar to the system dynamics, the subscript k dropped, so it's stationary. However, we add a term here, alpha to the power k, to represent that a cost occurred in the initial stage cost more than the cost occurred in the future stage. And the intuitively, you can interpret this as encode the effect of interest. For example, if you spend $500 today, as opposed you spend $500 in 2 years' time. If you spend $500 in 2 years' time, then today's $500 you can put into the bank and collect the interest. Then after 200 days later, you're gonna have interest in addition to this $500. So that's why the future cost of the same amount costs less in today's view. And this is called a discount factor, and it takes value from 0 to 1, including 1. And if alpha is strictly less than 1, the problem is called discounted. However, another reason that we introduce this discount factor typically is because it makes the mathematical problem well-defined. So given a policy, its cost, the cost of this policy is the limit of finite horizon problem with n stages as n goes to infinity. So the most ideal case, the best case where we have the nicest, the strongest theoretical result is when alpha is strictly less than 1 and the stage cost is bounded, by which I mean for this function stage cost g, for all x, u, and w, its absolute value is bounded by a given constant. And this type of problem is the main focus of our lecture. And in fact, the majority of reinforcement learning literature deals with this type of problem. So, and for similar as finite horizon problem, our focus is to find optimal cost function, J star of x0, which is minimizing over all pi. Recall that each pi is a sequence of functions, right? We want to find among all those infinite length sequence of functions, the one that minimize the cost. For problem with alpha equal to 1, in order to have this limit well-defined, so that the cost does not blow to infinity or so on, we typically include a special cost-free termination state. This means once the state xk reaches t, it's gonna stay there in all the future stages and it's gonna incur zero cost. One such example is shortest path problem. In shortest path problem, you can spin around in a circle node, move around. But we suppose that if all the nodes have access or have a path to the termination, the target state, which will be denoted as T, then it can be modeled as an infinite horizon problem with no discount, but it's a deterministic problem. It can also have the extension of stochastic version, which is called stochastic shortest path problem. And but in either case, what is needed is to make the assumption that under optimal policy, the cost is finite for all states. Yes? Sorry? Well, you can. I mean, that's part of, let's say, you have the same G, right? You have the same G and you add a discount factor, alpha K, then you call it G, K, XK, UK, and WK, right? So that's, yeah, you can still use it. It's not a monopoly for infinite horizon problem. You can include that. So, okay. All right, so for infinite horizon problem for theoretician, typically for people who like theory, it's very nice because it has a lot of nice mathematics to do. And the theorems that one aspires to prove includes analytical results and computational results. The three theorems. The first one is for infinite horizon problem, if we choke off, like cut off all the future stages and just consider from stage 0 to stage k, use the same stage cost and use the same system dynamics, we compute its optimal cost to go, which denoted by jk. What we want to show is whether or not this sequence of jk converge to the actual optimal cost J star as k goes to infinity. So where this Jk is the k stage optimal cost starting from x. Again, the same system dynamics and the same stage cost. We only consider k stages. We solve this finite horizon optimal control problem. The optimal cost to go, we denote by Jk. Then we include one more stage, k plus 1 stages. We solve this finite horizon optimal control problem, have Jk plus 1 and Jk plus 2 and so on. What we want to know is as k goes to infinity, whether or not this Jk converge to J star. By principle for optimality, the optimal solution of k stages can be used to compute the optimal cost of k plus 1 stages, right? How can we do that? We simply plug in this dynamic programming formulation because the k stage problem, the optimal cost is the tail subproblem in the k plus 1 stage problem. So through this iteration, we can compute Jk as k increases, and we want to know whether or not this thing converge to J star. In fact, this is what we call value iteration with a special initial condition that J0 equal to 0. So we want to know whether or not the sequence converge to J star. And as you may see that compared with our previous derivation in the finite horizon problem, the change here is we reverse the order of index starting from instead of starting from n, we start from 0, and we deal with this discount factor appropriately, and I will not go into detail. So the second thing we want to show is whether or not J star satisfies Bellman's equation. What does it mean? It means that Bellman's equation, it means that optimal cost satisfy this nonlinear equation. It's a scalar, it's one scalar equation for one x. So if you have 10x, then you need to solve those 10 scalar equations altogether. Not really scalar equation, 10 equations altogether. And if you have a zillion different x, you need to solve them all together. And if you have infinite x, you need to solve them infinitely many together, all together. And this formula is sort of intuitive because if we take the limit on both sides of this value iteration equation, and suppose that the limit of jk goes to j star, we take a limit on this side, we have j star, we take limit on this side, make the assumption that this limit can go all the way inside here, then we have j star again. As it turned out, this is the most reliable result in a lot of optimal control problems. So other theoretical result may not hold for some problem, but this results almost hold in all cases. Okay, there are some exceptions, but we will take it for granted that this result holds. That is, J star satisfies Bellman's equation. Now the significance of this is that, remember, what is J star? J star is the one that you minimize over the policies, right? Each policy is a sequence of functions, infinitely long sequence of functions. That's not easy, but suppose that we have only 10 different k, right? We have only 10 different x. So the state space includes 10 different x. Solve the original problem based on the definition of J star, then for each x, you solve this infinitely long minimization problem, try to find among all the policies the best, and each policy is a sequence of functions. That's not easy. However, if we solve, since we know, or we assume that optimal cost satisfies Bellman's equation, we can instead solve this Bellman's equation, which is 10 scalar equation, 10 dimension equation. So it becomes a finite dimension object we want to solve. That's much easier, right? So that's the significance of this result. The optimality condition states that if a function attains the minimum in the Bellman's equation for all x, then this policy, which is taking mu star in all stages, is optimal. And this type of policy is called stationary. So if a policy mu star attains this minimization minimum for all x, satisfies simultaneously for all x, this attains the minimum, then this policy, which we call stationary policy, is optimal. And this is much nicer because we don't need to remember which stage we are, right? We only need to see what is the x, and we plug into this function, we get a control that is optimal. Okay? And for solving J star in dynamic programming literature, there are several major algorithms, and the two most important ones are value iteration and policy iteration. So value iteration generates finite horizon optimal control cost function sequences by this iteration, where J0, in the previous slide, I said J0 is 0, right? But in many problems, J0 can be arbitrary. So starting from some arbitrary J0, you perform this iteration, it's going to converge to J star, but not always. So still some conditions are required. Alternatively, we have policy iteration. It generates sequence of policies and their cost functions mu k and j mu k, where mu 0, again, can be arbitrary in some problems. At each typical iteration starts with a policy mu and generates a new policy mu tilde in 2 steps. The first step is policy evaluation step, whereby we compute the cost function j mu of the policy mu, which we also call base policy. And then followed by the policy improvement step, whereby in place of J star, we plug in the J mu, the newly computed J mu, and get a new policy, which is mu tilde. So starting from mu 0, we perform policy evaluation step to compute J mu 0, and then plug J mu 0 here to compute mu 1. And then go back to the policy evaluation step to compute J mu 1, and then perform minimization to compute mu 2, and so on. So this is policy iteration algorithms. And note that in the policy evaluation step, we need to compute the cost function J mu. And it is equivalent to solve Bellman's equation for mu. So J mu, like the optimal cost, also satisfy a Bellman's equation, which looks like this. It drops the minimization calculation. You don't need to have the minimization calculation anymore, because given X, a control is selected by the given policy. So the cost function of this policy satisfies this Bellman's equation. And how to compute J mu? One way is to perform value iteration with respect to this policy. Essentially, drop this minimization here and use U. So start from some J0, drop the minimization, you perform this value iteration, eventually it will converge to J mu. One thing I want to emphasize is that this formula is linear in J mu. So unlike this minimization here, because the minimization, this equation is nonlinear in J, whereas here is linear. Alternatively, we can use simulation. Like, for example, if we don't really have mathematical formulas for all those expectations, for those distribution of random variables and disturbances, we may just run simulation in order to find samples of the random variable and to compute the expectation approximately. And you can also apply temporal difference method in other methods. One thing I want to emphasize is that the policy iteration can be done exactly as well as approximately. And in fact, approximate policy iteration is what people often refer to as self-learning. So starting from, let's focus on the exact policy iteration first. So starting with a base policy mu, we perform policy evaluation step in order to compute its cost function J mu. Then we perform policy improvement step, whereby J star, we use J mu in place of J star in the Bellman's equation and find the control that attains the minimum. And we do this calculation for all state. Through this process, we get a new policy, which is a rollout policy. Then we treat this rollout policy as the base policy and repeat this process. So for each step, for every X, we need to compute its corresponding J mu of X. So let's say there are finitely many X, 1 million. Then this J mu would be a million dimension vector or a lookup table. And similarly for the policy, it will be a million dimension lookup table, right? And the important fact, which we will discuss later, is policy iteration yields in limit an optimal policy in some cases. And it is faster than value iteration and can be viewed as Newton's method for solving Bellman's equation. Another thing is policy iteration can be implemented approximately. So I just mentioned that in the exact form, suppose that there are a million states. So this J mu would be a million vector. And say similarly, the policy dimension is also a million. What if the number of states is just too large or infinitely many? It's not possible to list every single one's value anymore. What we're gonna do is, suppose we have a policy, then instead of computing this J mu exactly, we run simulation in order to get trajectories of system under this policy, and then calculate samples of J mu, average them over, and have state cost function pairs. And those would be the value data we used to train a value network, let's say, to approximate this J mu. Then, after we get this approximate version of J mu, we perform one step look ahead to get the policy data. So instead of listing the control for every single state, again, we sample states. We do one step look ahead so that we're gonna have state control pair. Those would be the policy data. And we don't use those data to train the policy network. After the training process completed, we have a rollout policy mu tilde, which hopefully improves upon the base policy we start with. And we treat this rollout policy as base policy and repeat this process. This in reinforcement learning literature often is referred to as self-learning, because it's like this perpetual loop that just self-generating data, and after self-generating data, you train the neural network, you get something better, then it generate data for its own training again. So that's approximate implementation of policy iteration. Now let's go back to the linear quadratic problem and give some intuition about illustration about how the Bellman's equation looks like for infinite horizon problem as well as value iteration. We focus on deterministic case, and we consider this linear system, A, B are given constants and quadratic stage cost Q and R. And Bellman's equation for this formula, for this problem would look like this. The right-hand side, left-hand side and right-hand side involve the same function. Both is the same function. There's no stage anymore. And the same function should satisfy this equation where U takes value in real line as well. So what we said earlier, translate to this problem, is that the optimal cost of the linear quadratic problem involving k stages would look like this, would be quadratic function. And the first theorem says that this kk parameter should converge to k star, where k star is the optimal cost of the infinite horizon problem satisfy the Bellman's equation. And the optimal policy is also linear, where L star is obtained from Bellman's equation. So if we plug in this k star x squared to here and perform the minimization, essentially set the derivative with respect to u to 0, and we're gonna see that it's linear in x. So fix x become a parameter, become some constant, and we minimize over u, and this u that attains the minimum gonna look like this, that is linear in x. So to characterize K star and L star, we plug in Jx equal to Kx squared into Bellman's equation. And this formula looks like this. And we expand the square term and set the derivative with respect to u to 0. Exact calculation as in the finite horizon case, we're gonna end up in this formula, f of k times x squared, where f of k equal to this, again, identical to the finite horizon case, where the minimizing u equals to this. Now, here's something remarkable about linear quadratic problem. Remember, Bellman's equation says that we need to find a function that satisfies this equation for all x. In linear quadratic problem, how many x do we have? Infinitely many, right? Because this is a scalar problem. X can be anything on the real line. So the original Bellman's equation is really a functional equation because there are infinitely many formulas we need to solve, equations we need to solve. However, because of the favorable structure of this problem, that is the stage cost is quadratic and the system dynamics is linear, the Bellman's equation end up in this formula. If we start from some function k times x squared, the quadratic. So we cancel out those x squared on both sides. Essentially, Bellman's equation simplified as a scalar equation that only involve this quadratic parameter k. So the original infinite dimension problem become one dimension problem, which is solvable. And as you note here, it's nonlinear, right? It's because the denominator involves k, so it's nonlinear. So the original Bellman's equation is solved by a quadratic function where k star being the solution of Riccati equation. This is what we call in control literature referred to as Riccati equation. So which essentially is Bellman equation with function restricted to quadratic functions. And the optimal policy is linear in X, where here are also closed for formulas. So how does Riccati equation looks like? Well, or if we plot out this f of k, it looks like this, which is this red curve. It's, for one, it's nonlinear. Two, it has this asymptotic, something laid out from my computer or, okay. So I have two asymptotics. One is as k goes to infinity, it approaches this value. Second is as k approaches to this value so that this thing become arbitrarily small, it goes to minus infinity. And the shape of this Riccati function is concave. It means if you take any 2 points on the curve and draw a line segment, this line segment would lie below the curve. So if we want to solve the Riccati equation, we can actually solve by drawing the plot, essentially. So we draw the figure of the left-hand side, which is k equal to k. So given the horizontal axis is k, we want to know what is the value of the left-hand side, which is k. So it's a 45-degree line. And on the right-hand side, we have f of k. So the solution is where those two equation, those two curves lines meets, right? That's K star. And if we visualize the value iteration algorithm applying to this problem, essentially it's that starting from some K0 at a typical iteration KK, we set K plus 1 to be f of KK. So what is it? We simply look on the curve, what is the value of this f of KK by setting the horizontal here to be KK and see, okay, here is the value. So what about K plus 2? We plug in this value to here in order to get K plus 2. And the value K plus 1 can be obtained by drawing a horizontal line to meet with 45-degree line. And this is where K plus 1 is. And then we find out K plus 2. As you may see, the value iteration in this case corresponds to this staircase construction. And this staircase construction eventually going to lead us to K star. And the same goes for starting from this side. So if you draw the staircase construction, you're going to see eventually it goes to this K star as well. So this is a visualization of value iteration. In some cases, it converges fairly fast, and in some cases, it can be slow. For example, here we have this curve, very much bending, right? But if suppose we have a curvature which is very flat, very, very flat, almost 45-degree, parallel with 45-degree line, then it's going to take you a long time to eventually get into this point. By contrast, policy iteration typically is faster, and we're going to use the same figure to visual, like the same one-dimensional figure to visualize why it is the case. Any questions?
Yeah.
Yes, please.
What the significance of the K part is actually related to that?
That's a good question. There's no significance. That's nothing to do. It's another solution of Riccati equation, but it has nothing to do with optimal cost because it's negative, and intuitively every stage cost is positive, and you expect the infinite horizon cost to be positive. So it has nothing to do with our original problem. Yeah. Yeah. And typically, for a given problem, people would start with K0 equal to 0 and do the construction, staircase construction to find K star. Okay. Any other questions? All right, so this concludes the first half of our overview lectures, 4 of them in total. And for the next 2 lectures, we're going to emphasize Newton step interpretation using linear quadratic problems as a vehicle. Generally, approximation in value space is the Newton's method for solving Riccati equations, starting from the cost approximation. And the rollout method that we're going to focus on, and we have covered already in today's lecture for the finite horizon deterministic problem, is 1 Newton step starting from some base policy cost. And policy iteration consists of repeated Newton step. In the 4th lecture, we're going to focus on problem formulation and reformulation. So dynamic programming, despite being a very useful and broadly applicable tool, part of the art is how to formulate a practical problem as a dynamic programming problem. And we're going to cover a few different classes of problems involving terminal state, including shortest path problems. So how do we formulate this problem as a dynamic programming problem? What about if there are delays involved in the problem? For example, this xk at stage k, you will only have access to it after 5 stages. How can we deal with this problem? What if the random quantities are correlated? How do we deal with this? What about, let's say we have some information that tells us what's going to happen in the future, that give us an edge to perform control selection. How do we deal with this? All those things can be dealt with properly by using the state aggregation, augmentation technique. Also, problems involve imperfect state information, the POM DP problem. How do we formulate that? And problems with multiple agents, and problems with continuous state space, and problems with unknown or changing parameters. So all those things will be covered. Well, for the homework, please read as much of the textbook as you can. And the second homework, which due in 1 week, is exercise 1.1 B and C of the textbook. Okay. Thank you for your attention.